Good morning everybody. Today we shall start with a new topic, moment of inertia, or what we call as second moment of area. So let's just define the moment of inertia first. It is defined as the sum of individual It is defined as the sum of second moment of area of individual sections about an axis. So to understand this definition better, we shall consider a area or an arbitrary area named as capital A. So within this area we will select some 3 smaller elementary areas. We shall name them as A1, A2 and A3. So as per the definition, it is sum of second moment of area of individual sections about an axis. So first of all, we shall see that we will consider some small elementary sections within this whole area. So amongst that, A1, A2 and A3 are the small elementary areas. So we will have to see that these areas are placed at some distance apart, right? So here is the reference axis OX and OY. So to understand where A1 is located, it is located at some distance apart from x-axis. A2 is located at some distance apart from x-axis and A3 is located at some distance apart from x-axis again. So we will give some name to these distances. The distances are named as y1, y2, y3 respectively. So these are the distances with the reference of x-axis, right? Similarly, we will mark the distances with respect to y-axis as x1, x2 and x3 respectively. So now we shall take moment of the area with respect to x-axis. Then Ixx is equal to A1 into Y1 plus A2 into Y2 and A3 into Y3. So, we shall remember this is the first moment. But as per our definition, to define moment of inertia, we'll have to consider the second moment of the area. So, taking moment again, we'll write it as Ixx is equal to A1 into square of the distance, A2 into Y2 square and A3 into Y3 square. So here is how we are summing up of all the moment of areas. So finally we can write that as A into Y square, right? Therefore Ixx is equal to A into Ixx is equal to A into Y square. Similarly, if we consider Y axis, then Iyy is equal to A into X square. So this is how we consider the moment of inertia with reference to the reference axis. So which are all the reference axes here? OX and OY. So means to tell that these areas would be considered based on the reference axis. So now moving on to the next concept. Radius of gyration. It is defined as that distance from the axis up to a point where the area is concentrated. To understand this again, we'll consider an area wherein we consider some small elements, naming that as A1, A2 and A3. So, if we are considering the reference axis, A1 is placed at some distance apart, Y1 from x-axis, at some distance apart, that is Y2 from x-axis, and Y3 is the distance of A3 from x-axis. Similarly, we are locating the distance of A1, A2 and A3 taking Y as the reference, and we shall denote that as x1, x2 and x3 respectively. So here, as per our definition, we are considering that in spite of these elementary areas being dispersed, we'll consider that all the areas have been concentrated at some point. So for that, we'll take an example considering that area is concentrated at a common point. So, it is located at a distance apart from x-axis. So, this is radius of gyration. So, all what we can understand here is that in spite of the areas being dispersed here, it is being concentrated at some common point. So, this elemental strip that we have considered is at a defined distance from the reference axis. So, as per this diagram, we write the moment of inertia as Ixx is equal to the area into the square of the distance. But all we have written here is about one area. So, if we sum up all the areas, again it will be A into k square, while k can be written as Ixx by A. So, this is the radius of gyration considering x as the reference axis. Similarly, if we are considering y axis as the reference, then it is written as square root of Iyy by capital A. Next, moving on to the polar moment of inertia. Polar moment of inertia. So, all we have dealt as of now is about two reference axes, x and y. So, we know that the area is fixed within two axes. So, here we consider one more axis, that is a third axis, and name that as z. So, this is the polar moment of inertia. So, what we can observe here is that the third axis, whatever we have considered, is perpendicular to the lamina or the area that we have considered. Similarly, the other two axes. Fine. So, now to understand the polar moment of inertia in a better way, the polar moment of inertia is represented as Izz or Ip or J. So, on the whole, we can tell that polar moment of inertia is perpendicular to the given lamina. So, the axis that is perpendicular to the given lamina represents the polar moment of inertia. The next is perpendicular axis theorem. The theorem states that axis this theorem states that moment of inertia of an axis perpendicular to the plane is equal to the sum of the moment of inertia of two mutually perpendicular axes. So, we will understand that with a diagram. Here is the total area divided into n number of small elementary areas. Here is the reference origin, OX is the reference axis, OY is one more reference axis, of which we will consider one small or one elemental strip. So, in order to prove this theorem, we shall consider an elemental strip. Therefore, the moment of inertia of the strip about an axis is equal to OZ is equal to area into R square. So, these are all the small areas represented by dA. As we have understood that we have an axis that is perpendicular to the plane and we have named that as small r. So, as per the definition, that is to write the second moment of area, we consider the area into square of the distance. So, now the moment of inertia of the whole area is about an axis is given by IZZ is equal to what is R square here? It is x square plus y square. So, upon opening the brackets, we get summation of dA square plus summation of dA square, dA into x square plus summation of dA into y square. As per the definition of moment of inertia, we know summation of dA into x square is ax square plus ay square. So, we can represent that as Iyy plus Ixx. So, here is that Ixx is equal to Iyy plus Izz, that is the moment of inertia of an axis perpendicular to the plane is equal to sum of the two mutually perpendicular axes. So here we have x and y axis that are mutually perpendicular, and here is the axis that is perpendicular to the plane. Moving on to parallel axis theorem. It states that the moment of inertia about an axis parallel to the centroidal axis is equal to the sum of the moment of inertia about the centroidal axis and the product of area and the square of the distance between the two axes. So to understand that in a better way, we'll draw a diagram. X and y axis. We select an elemental strip. This is the centroid represented by point G. So axis that passes through the centroid is the reference axis. We'll name that as XX. So the axis that passes through the centroid is the centroidal axis. And we have one more axis that is parallel to the centroidal axis. We shall name that as AB. So now here is the distance between the elemental strip and the centroidal axis. We'll name that as Y, and the distance between the two axes is Y bar. So now as per the definition, we'll have to prove that IAB is equal to IXX plus A into Y bar square. So how do we prove that? Taking moment of inertia about an axis parallel to the centroidal axis, that is IAB is equal to area into square of the distance. So what is the distance that we are supposed to consider? It is y plus y bar. Therefore, it is square of the distance. Next, taking moment of inertia about the whole moment of inertia of the whole area is equal to IAB summation of dA into y plus y bar whole square. So, we get summation IAB is equal to summation of dA into y square plus y bar square plus 2y into y bar. So, upon simplifying, we get summation of dA into y square plus summation of dA into y bar square plus 2y into summation of dA into y, 2y bar into summation of dA into y. So, now summation of dA into y square is Ixx plus summation of dA into y bar square is ay bar square, while this term will be 0 as summation of dA into y, that is moment of inertia about the centroidal axis, is 0. So, this has to be noted. Then we have Ixx plus ay bar square. Therefore, IAB is equal to Ixx plus ay bar square. We can just see that moment of inertia about an axis parallel to the centroidal axis is equal to sum of the moment of inertia about the centroidal axis and the product of area into square of the distance between the two axes. Now, we shall move on to derive certain expressions for different laminae or generalized areas. So, the moment of inertia for some of the generalized area. Derivations to find out moment of inertia for some of the areas. We consider the rectangular lamina under that. First one is to find out moment of inertia about the centroidal axis. So, we draw a diagram of a rectangular lamina symmetric about y axis and x axis, centroid represented as capital G. We select one strip of the whole area So, we will have to note that we can get n number of these type of strips throughout this area. The thickness of the strip we have selected is dy. The dimensions of the lamina is breadth b, depth d. We will denote the axis as xx and yy. The distance is y bar. So, distance from the centroidal axis up to the reference axis is y bar. So, now we shall consider the area of the elemental strip first. Considering the area of the elemental strip as, since it is a rectangle, b into dy. So, moment of inertia of the elemental strip about an axis. So, this is the reference axis that we have noted down here, is moment of inertia of the elemental strip about an axis is equal to area into square of the distance. So, the distance is from the elemental strip up to the centroidal axis and we name that as y. So, now moment of inertia of the whole area is equal to, since it is the whole area, from minus d by 2 to plus d by 2 b into dy to y square. Further, b is a constant, upon minus d by 2 and plus d by 2 we have y square dy. Further, integrating y square dy upon the limits of minus d by 2 and plus d by 2, we get y cube by 3 upon the limits of minus d by 2 and plus d by 2. So, further we get y cube by 3. So, I will take the 3 out. So, y cube means d by 2 whole cube minus of minus d by 2 whole cube. So, further we get b by 3 into d cube by 8 plus d cube by 8. Therefore, upon simplification we get eight d cube plus 8 d cube, that is b by 3 into 16d cube by 64. So, upon further simplification, we get bd cube by 12. Therefore, moment of inertia about the reference axis for a rectangular lamina is bd cube by 12. Similarly, if we consider the elemental strip to be along the vertical point, that is, if we consider the elemental strip as such, then we get Iyy is equal to db cube by 12. The next derivation, the next expression, moment of inertia of the rectangular lamina about the bottom edge. So, we shall draw a diagram . Symmetric about x and y axis. All we want is to get the expression if we consider this axis, we have named that as 1, 1. Similarly, if we consider this side, then it will be named as I, 2, 2. Therefore, here is the breadth, the depth d, the centroidal point G. So, now we know that we select now here is the centroid of the given lamina. The centroid is between the centroidal axis and the considered axis. So, now we have to apply parallel axis theorem to get the expression. So, how do we know that we are supposed to apply parallel axis theorem? So, we can just see all we want is about that is the moment of inertia about this axis, and the axis is parallel to the centroidal axis. So, by applying the parallel axis theorem for these two axes, we get the expression for the required axis. So, by applying parallel axis theorem, so we can find out the moment of inertia, that is the expression for this axis, by applying the parallel axis theorem. So, what does the parallel axis theorem state? It is, as per the diagram now, this is the required axis, that is the moment of inertia of this axis is required. I11 is equal to Ixx. So, here is Xx moment of inertia about the axis parallel to the centroidal axis is equal to sum of moment of inertia about the centroidal axis, that is Ixx, plus area into square of the distance between the two axes. So further, we know Ixx is equal to BD cube by 12 plus area of the rectangle B into D into centroid of the lamina. Centroid of the rectangle is D by 2. So we are writing that as D by 2 whole square. So now upon simplifying, we get BD cube by 12 plus B into D into D square by 4. Therefore, further simplifying, we get BD cube by 4. So now we get 4BD cube plus 12BD cube, that is equal to 16BD cube by 48. So finally we get BD cube by 3. Therefore I11, that is moment of inertia about I11 is equal to BD cube by 3. Similarly, if it is with respect to I22, that is if we consider this edge, then the expression will take the form dB cube by 3. So the next expression is for polar moment of inertia. So as per the definition, Izz is equal to Ixx plus Iyy. We know Izz is the polar axis, Ixx is BD cube by 12, Iyy is dB cube by 12. So upon further simplification, we get D square plus B square by 12. Suppose if the lamina is a square rather than rectangle, then B will be equal to D. So Izz will be B into B, B square plus B square by 12. So this takes the form of B square into 2B square by 12. Therefore, it is 2B to the power of 4 by 12 or B to the power of 4 by 6. Therefore, Izz will be B to the power of 4 by 6. The next expression is for a hollow rectangular lamina. So we will consider an hollow rectangular lamina. of dimensions B into D, while here it will be represented as small b and D. So now Ixx is equal to BD cube by 12 minus BD cube by 12, or 1 by 12 into BD cube minus BD cube. Similarly, Iyy is equal to 1 by 12 into dB cube minus dB cube. We derive the expression to find out the moment of inertia of a symmetric triangle. So, we will consider a symmetric triangle, name that as A, B and C. The base is B, height represented as h. So now to find out the expression for the whole triangle, we shall divide the whole area into small strips, of which for deriving we will consider one such small strip. The thickness is dy and the base is denoted as B dash. We shall name this small triangle as CA dash into B dash, while the height here is y and the remaining is h minus y. Therefore, in order to get the expression, we shall compare the two triangles which we can see here. So, from the principle of similarity of triangles, we can derive the expression to find out the moment of inertia of a symmetric triangle. So, by similarity of triangles CA dash B dash and CAB, so we will compare the height and breadth of the said triangles. So now the height of the bigger triangle is h, while the smaller one is h minus y. The base here is B and B dash. So we can cross multiply and get the expression for B dash as B by h into h minus y. So now we have got an expression for B dash. We will name that as equation 1. So now considering this elemental strip, the area of the elemental strip, as it takes the form of a rectangle, it is B into dy. But we have considered the base of the smaller triangle, we have denoted that as B dash. Therefore, it is B dash into dy. The area of the elemental strip that we have considered here takes the form of a rectangle, and we have taken the area as B dash into dy. That is what we have written it here. Substituting equation 1 here, B by h into h minus y dy. So now the moment of inertia of the elemental strip is equal to area B by h into h minus y into dy into square of the distance. So this is the distance, it is y square. So now the moment of inertia of the whole area about AB. So we have considered this as the reference. So we have written it here as about AB. We get B by h into h minus y dy into y square. We have to integrate that upon the limits of 0 to h. Further, upon integrating, we get from 0 to h. So now we know hy square into dy minus y cube into dy. So upon integrating, we get y cube by 3 upon 0 to h minus y4 by 4 from 0 to h. So now we get B by h to h cube by 3 minus h to the power of 4 by 4. Therefore, B by h into h to the power of 4 by 3 minus h to the power of 4 by 4. Further, B by h into 4h cube minus 3h to the power of further B by h into 4h to the power of 4 minus 3h to the power of 4, which will be h to the power of 4 by 12. So we get bh cube by 12. Therefore, the moment of inertia about AB is equal to bh cube by 12. To get the expression about the centroidal axis, apply parallel axis theorem. Then IAB is equal to IXX plus A into square of the distance. So, what is the square of the distance that we have to consider? If we are considering a centroidal axis, so we will consider this as the centroid. So, here is the centroidal distance that we have represented that as y bar. So, square of the distance between two axes. So, now for the IAB is equal to IXX plus area of the triangle is half into B into H. Next is the centroid of the symmetric triangle above the base is H by 3. Therefore, it is H by 3 whole square. Finally, we get IAB is equal to IXX plus half into BH cube by 9. Or IAB is equal to IXX plus BH cube by 18. So, this is the expression if we have to find out the moment of inertia about the centroidal axis. So, the expression will take the form of BH cube by 12 if we consider the bottom edge of the area, bottom edge of the lamina. Expression to find out the moment of inertia of a circular lamina. We will consider a circular lamina, symmetric about all the axes. The radius is R, the reference center is O. So, we will consider one small ring, it is elemental ring, the radius of that is R, the thickness being dr. So, now to derive the expression, we will consider the area of the elemental string. So, first of all, let dA be the area of the elemental ring, then dA is equal to 2 pi r into dr. Since it is a circular lamina, we will consider the polar moment of inertia. Therefore, polar moment of inertia of the elemental ring is equal to area represented as dA into square of the distance. So, here is the radius, substitute the value of dA here, 2 pi r dr into r square. So, that will take the form of 2 pi r cube into dr. So, now polar moment of inertia of the whole circle is equal to integral of 0 to r 2 pi r cube dr. So, upon integration 2 pi is the constant. So, integrating r cube dr within the limits of 0 to r, we get r to the power of 4 by 4. So, now we get pi r to the power of 4 by 2. Therefore, the polar moment of inertia of the whole circle is pi r to the power of 4 by, that is Izz is equal to pi r to the power of 4 by 2. If expressed in terms of diameter, then Izz is equal to pi expressing r in terms of diameter, then we get pi d to the power of 4 by 32. We know that Ixx is equal to Iyy for a circular lamina. Then Izz is equal to Ixx plus Iyy as per the definition of polar moment of inertia. Since we know that Ixx is equal to Iyy for a circular lamina, then Ixx is equal to Iyy will take the form pi d to the power of 4 by 32. Then Ixx is equal to Iyy will be pi d to the power of 4 by 64. Moment of inertia of a hollow circular lamina. See, if we consider an hollow circle, then R, here is the capital R, then this expression will take the form, of Ixx is equal to Iyy is equal to pi by 64 into d to the power of 4 minus d to the power of. Now, the next expression is moment of inertia of a semicircle. So, we will write the diagram. symmetric about y-axis. Here is the radius, the centroidal point represented by 4r by 3 pi. So, this is y bar. We shall write the axis here as xx denoted by the centroid G. Since this is a semicircle, we write the moment of inertia of a semicircle as half of the moment of inertia of the regular circle. So, IAB is equal to moment of inertia of a circle into half. What is the moment of inertia of a circle? That is for the whole area. It is pi d to the power of 4 by 64 into half. That takes the form of pi d to the power of 4 by 128. So, moment of inertia about the axis selected at the bottom named as AB is equal to pi d to the power of 4 by 128, where d is equal to 2r. If we are supposed to represent that in terms of radius, then we will substitute d as 2r. Now, whatever the expression that we have got here is about AB. What if we want the expression about the centroidal axis? Then, about the centroidal axis, then apply parallel axis theorem. Therefore, IAB is equal to IXX plus A into y bar square. Wherever IAB is there, I write that as pi d to the power of 4 by 128. IXX is retained. Area of the semicircle pi d square by 8 into centroid of the semicircle is 4r by 3 pi whole square. So, further pi d to the power of 4 by 128 is equal to IXX plus pi d square by 8 into r is equal to d by 2. So, it is d by 2 by 3 pi whole square. Therefore, pi d to the power of 4 by 128 IXX plus pi d square by 8 into 2d by 3 pi whole square, or IXX plus pi d square by 8 into 4d square by 9 pi square. Further, IXX plus d to the power of 4 by 18 pi, that is pi d to the power of 4 by 128, or IXX is equal to 0.00 0.68 d to the power of 4. So this is the expression to find out the moment of inertia about the centroidal axis for a semicircle. Lastly, moment of inertia of a quarter circle. So, we will consider the quarter circle, the centroid being 4r by 3 pi and 4r by 3 pi from either ways. This is x and y. Then if we consider this as AB, IAB is equal to pi d to the power of 4 by 256, where d is equal to 2r, or Ixx is equal to 0.00343 d to the power of 4. If we consider the centroidal axis. So if we consider this axis, we will have to use this expression, while if we are supposed to get the expression for the centroidal axis, then use 0.00343 d to the power of 4.